Good morning, students. Today we'll discuss about drago's rule. What is drago's? So drago's rule is telling about some molecules do not undergo hybridization. The central atom of some molecules do not have hybridization. How is that possible? Yes, it is possible. This is the empirical rule. This rule may not be 100% correct, but this rule has applications. Let us discuss. Suppose you take NH3. So NH3 you can write as N 3 single bond H with 3 hydrogen atoms and 1 bond. So take PH3, take ASS3. Then you take SBS3. So if you see NH3, in NH3 if you want to find hybridization, then you can apply the formula. Steric number is equal to surrounding atom plus half into ground state valency electron of central atom minus valency of surrounding atom plus or minus charge if any. Okay. So this formula let us apply for NH3. The surrounding atom how many? 3. 3 hydrogens are there? 3. Plus. Suppose you take G. Ground state valency electron of central atom. Nitrogen. Nitrogen valency shell electron how many? Nitrogen belongs to group 5A. So 5 valency electrons. So 5 minus. What is the valency of surrounding atom? Hydrogen valency is the 1. There are 3 hydrogen atoms. So valency is 1 into 3 hydrogen atom. Means you have to take valency of surrounding atoms all. So 3. So it's coming 3 plus 5 minus 3, 2 by 2, 1 equals to 4. So it is having 3 bond pair and 1 lone pair, steric number 4. And what should be hybridization? Hybridization of ammonia is sp3. Okay. So ammonia hybridization is sp3. What is the bond angle of ammonia? Bond angle is 170. What is the bond angle of pH3? It is approximately 93. Bond angle of ASS3, HASH bond angle is 92 degree. HSBH bond angle is 91 degree. Okay. So bond angle decreases. Yes, bond angle decreases. We studied in BSc-PR theory when electronegativity of central atom decreases, the bond angle also decreases. Yes, it is decreasing. And this is applicable for same number of bond pairs and lone pair species. Yes, this is applicable. So electronegativity decreases from nitrogen to antimony. So if electronegativity decreases, the bond pairs remains away from central atom. So if bond pairs remains closer to central atom, greater repulsion. If electronegativity is more, it will remain closer to central atom, greater repulsion. If it goes away from central atom, if electronegativity decreases, then bond pair goes away from central atom or not? So bond pair goes away from central atom. If bond pair goes away from central atom, so repulsion between bond pair decreases. Okay. So repulsion between bond pair decreases. In all case, lone pair bond pair repulsions are equal. And repulsion between bond pair decreases. So bond angle decreases. Is correct. But what is the problem? Problem lies here. If you go from NH3 to PS3, the bond angle decreases by how much value? Around 14 degree. The bond angle decreases by 14 degree. But if you go PS3 to SS3, the bond angle decreases by 1 degree. Here bond angle decreases by 1 degree. Okay. So here so much decrease in bond angle. Here the bond angle decrease is very small. Okay. Now these all angles are close to 90 degree. These all angles are close to 90 degree. These three. Similarly, let us take the case of water. Suppose we are taking H2O. Okay. Suppose we are taking H2O. Say we have taken H2O. The bond angle is what? In water, we have two lone pair and two bond pair. Again, H2S you take, two lone pair, two bond pair. H2AC you take, you will have two lone pairs and two bond pairs. H2TE you take, you will have two lone pairs and two bond pairs. And let us find the steric number. What is the hybridization? How two lone pair, two bond pairs? So steric number is equal to surrounding atom. Surrounding atom of H2O is 2. Okay, 2 plus. So surrounding atom H2O is 2. Then we will check the half into ground state valence electron. Ground state valence electron of oxygen atom is 6 because it is belonging to 6A. Valency of surrounding atom. Hydrogen valence is 1. So 1 into 2. Charge. There is no charge, no electron gain, no electron lost. So X is 0. So if you apply, it's coming 2 plus 6 minus 2, 4 by 2. So steric number is coming 4. Steric number 4, here surrounding atom is 2. So bond pair 2, lone pair 2. Steric number 4 means hybridization will be again sp3. Okay. Then what Drago has told? Drago has told for these three there is no hybridization. Similarly, for these three there is no hybridization. He will let us justify what he has told. Why? What is the logic behind it? So in water, the bond angle you see, water bond angle is 104.5 degree. And H2S bond angle is around 92 degree. Approximately I am taking. H2AC is around 91 degree and this is 90 degree. So you see the bond angle decrease how much? 12.5 degree. The change in bond angle is very high. And now if you see the change in bond angle in the next case, the change in bond angle is 1 degree. Here also 1 degree. So change in bond angle is not much after H2S. So these all bond angle are close to 90 degree. Okay. So now let us come to the Drago's rule. So this is about the bond angle variation. So what Drago has told? Drago has told 3 points. So point number 1 is, right, point number 1. Point number 1. So point number 1 he told, when central atom of covalent compound is from third group or above, if central atom of a covalent compound is from third group, or third means group 3A, means third group or above, means group 4A, 5A, 6A and 7A. Okay, 7A. The s orbital, the s orbital, the s orbital becomes pure and bonding will take place through pure orbital, through pure orbital. That means no hybridization. But it should follow condition number 2 and 3. So no hybridization will occur if condition number 2 and 3 are also followed. What is condition number 2? Condition number 2 is if electronegativity, if electronegativity of if electronegativity of surrounding atom, central atom, electronegativity of surrounding atom should be less than, we can write surrounding atom also, surrounding atom less than or equal to 2.5. Central atom should be more than 2.5. Okay. And third condition is also there. Third condition is that central atom should contain central atom should contain at least one lone pair. Okay, मतलब क्या है कि central atom belongs to these groups. This is condition number 1. Condition number 2, if electronegativity of surrounding atom is less than 2.5. Condition number 3, if central atom should contain at least one lone pair, एक से ज़्यादा lone pair is there. Here central atom contains one lone pair, and here central atom contains two lone pairs, and surrounding atom hydrogen electronegativity is 2.1. So electronegativity of surrounding atom should be less than or equal to 2.5. If this is there, then no need of considering hybridization. Then no hybridization, no hybridization for central atom. Now see, so what Drago has told, if these three conditions are fulfilled, these three cases, there will be no hybridization. Here there will be hybridization sp3, and here hybridization sp3, here hybridization sp3, but here no hybridization. So why no hybridization? So this is explained by Drago. So how Drago has explained? So Drago has explained that in these cases the bond angle is close to 90. This bond angle is close to 90. And this is possible if and only if they have no hybridization. If they have hybridization, the bond angle cannot be close to 90 degrees. Now suppose you assume that the bond angle is 90 degrees. Then what is the bonding? Okay. And assume that there is no hybridization. So now let us take PH3. PH3. Okay. Phosphorus electronic configuration atomic number is 15. So 1s2, 2s2, 2p6, 3s2, 3px1, 3py1 and 3pz1. Suppose there is hybridization, then sp3 will be mixing. Okay. Now simultaneously we will check the hybridization of ns3. ns3 there is hybridization. So the bond angle changing is very less. Suppose you see in sp3 hybridization tetrahedral structure of methane. CH4, CH4. What is the bond angle? 109.5 degree. And now NH3 having one lone pair and three bond pair. Suppose you take NH3 one lone pair and three bond pair. The bond angle is lesser than 109.5 degree. Why? Because lone pair bond pair repulsion is more than bond pair repulsion. So obviously if lone pair bond pair repulsion is more, then the bond will be contracted and the bond will be reduced. The bond angle will be less. Because this repulsion is more, this X repulsion is more than Y. So obviously Y angle will be less. So it is decreased, but decreased by less amount, around 2 degree, 2.5 degree decrease. But here the decrease is tremendous. From tetrahedral angle decrease is around 16.5 degree. It is very high decrease. Okay. So in NS3, your hybridization is sp3. Let us do hybridization nitrogen 7, 1s2, 2s2, 2px1, 2py1, 2pz1. So there will be hybridization of sp3. This was the hybridization. Okay. So if it is sp3 hybridization, then you will get hybrid orbital sp3, 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 sp3. So you will get 4 hybrid orbital due to sp3 hybridization. Out of 4, one is having paired electrons, so it will remain as paired. Okay. So this should be paired like this. But these are unpaired electrons. But they are hybrid orbital. sp3, 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 sp3. Now, when hydrogen is forming bond in NS3, you will get H is forming bond. This is hydrogen forming bond, so sigma bond is bond. So unpaired electron becomes paired. Again, one more hydrogen forming bond, sigma bond, and one more hydrogen is forming bond, sigma bond. So unpaired electron becomes paired. Okay, but in this case, hybridization is not there. If hybridization, suppose you assume that there is no hybridization, then you will have 3s2 like this, and 3px1, 3py1, and 3pz. Right. So if there is no hybridization, there will be no hybrid orbitals formed. So pure px, pure py, pure pz will remain. So if pure px, py, pz will remain, then how they look like? They look like this. Px in x-axis, suppose you assume 3 axes. X-axis, this is px, this is x-axis. Next, you take y-axis. Okay, so let us assume y-axis. Now in y-axis you take this py, and this is say y-axis. Now suppose you take z-axis. Z-axis is perpendicular to x and y plane. So that you take again z-axis. So z-axis is like this. different color. So z-axis is like this. So it will be z-axis like this. So 3 points. So x, y, and z-axis are like this in 3 coordinates. Okay. Suppose this is x-axis, this is y-axis, this is z-axis, and these 3 coordinates are perpendicular to each other. So this is px, and say this is py, and this is say pz. Now suppose 3 hydrogen will overlap. Hydrogen will overlap like this. Hydrogen will overlap like this, and hydrogen will overlap like this. So they will overlap, and they form sigma bond, sigma bond, sigma bond, and sigma bond. Okay. So 3 hydrogen will overlap, forming 3 sigma bond with px, py, pz. How? You can see the orbital diagram. So 3 hydrogen will overlap and forming sigma bond. Okay, forming sigma bond. Let us see. So 1 hydrogen will overlap here, another hydrogen will overlap here, and third hydrogen will overlap here. Means px, py, pz are 90 degree. They are close to 90 degree. Okay, all three axes are exactly 90 degree. If they are, if the bond angle are close to 90 degree, if they are pure orbital, then only they can overlap like this, and they form a bond angle is equal to close to 90 degree. If the bond angle is close to 90 degree, we can say they are not hybridizing. If they are hybridizing also, that we can say up to less extent. If the bond angle is violated from 90 degree, then we say they are hybridizing, but that is negligibly small. That is very less extent. Or we say they are not hybridizing, that's why the bond angle is 90 degree. Suppose they are hybrid orbital, you will get one lone pair. Okay, in NH3 one lone pair and 3 bond pairs will get. If 3 bond pair will get, definitely lone pair bond pair repulsion will be different. If lone pair bond pair repulsion is X, and bond pair repulsion, if suppose these 3 are bond pair, this is lone pair and these 3 are bond pair. So the bond pair repulsion will be different from lone pair bond pair repulsion. So bond angle will reduce by small amount. So here it is coming 107 degree around. But if there is no hybridization, then only the bond angle will be 90. If there will be pure p orbital, that is px, py, pz, then only they will overlap like this, and the bond angle will be 90. If px, py, pz are lying in 3 axes, then only bond angle will be 90. So Drago has assumed that in these 3 cases no hybridization, and in these 3 cases also no hybridization. So there will be pure p orbital. So next, this assumption is verified by some mathematical formula. How it is verified by some mathematical formula? Let us see. So next, I'm going to next page. So there is a formula for hybridization. Cos theta is equal to s upon s minus 1. That is equal to p minus 1 by p. Whereas theta is between 90 and 180. So 90 degree to 180 degree. 180. So if the bond angle we take, if suppose we are taking bond angle is 93 degree. If theta is equal to 93 degree, then you apply cos theta. Okay, is equal to cos 93 degree, and you solve s upon s minus 1. If you solve this, and it will be coming around 3%. The percentage of hybridization is, percentage of S character is around 3%. So suppose we are taking pH3 bond. pH3 bond, let us assume H is this, again one more this, and one more is along Z axis. Suppose this is X axis, this is Y axis, this is Z axis. pH3 is not having hybridization, and suppose this lone pair is pure s orbital. This is pure s orbital. If 3H are px, py, pz axis, and then percentage of hybridization is coming 3%. So percentage of s character for this px, py, pz, if it is no hybridization, will be 0, close to 0. if percentage S character of this bond angle 93 degree, this is 93 degree, okay. So pH bond angle 93. So in this bond angle, the percentage S character is coming 3%. If this is 3%, then this will be percentage S character will be 97%. That means we can assume 97 is close to 100. So this is pure S orbital. Okay. In PS3, the lone pair is pure S orbital and the angle is 93, means here only 3% hybridization. Okay. So this is only 3% hybridization and this is 97% hybridization. So this bond angle will come 93 degree if and only if there is no hybridization. If there is hybridization, suppose we consider hybridization. In NS3 there is hybridization. Okay. If there is hybridization, what is the hybridization? sp3 hybridization. If sp3 hybridization, what is percentage S character? Percentage S character is 25%. So if percentage S character is 25%, it is not 100%, then it is hybrid orbital. Cannot be pure p orbital. But here the bond angle is 93 degree coming. So the percentage of S character is coming 97%. Then only it is assumed. So in order to prove that bond angle is 90, the percentage of S character in lone pair is 97%. Percentage of S character in this overlapping orbital is 3%. If it is 3%, then it should be pure p orbital, 3% or close to 0%. So this has to be pure p orbital. If it is pure p orbital, then only there will be no hybridization. Okay. Now next question arises: what is the evidences for this? So this is the assumption. Now what is the evidences? I am going to next page. What is the evidences for this? Yes, evidence is there. I tell you evidence. Evidence number one, we can say the solubility. Okay. So if you take NS3 and you add with water. So this is highly soluble. Highly soluble. Now you take PS3. If you add with water at room temperature, it will not be soluble. It is not soluble. So this is explained on the basis of Drago's rule. How explained? In NS3, we have assumed the hybridization is there. In PS3, there is no hybridization. If there is no hybridization, here the lone pair, whichever is there in phosphorus, is pure S. Means percentage S character is more. So we have studied in periodic properties is that more the percentage S character, more will be electronegativity. So more the percentage, the S character, more will be electronegativity. If more will be the electronegativity, it will be taking electron. It will not liking to give electron. It will be taking electron. So if it will be taking electron, it will be less basic. It will be less basic. And it will not share its electron to hydrogen, or it will not share its electron to acid, then PS3 cannot react with, PS3 does not react with HCl. So PS3, if you take dilute HCl, no reaction. But if you take NH3, dilute HCl, there will be highly reaction and it will give you NH4Cl. This will be reacting fast. But if you want reaction with HCl, then you have to give concentrated HCl, then it will be reacting up to very less extent and giving you PH4Cl. So if this is weak base, then it will not react with HCl. If it is strong base, it will highly react with HCl. So in NH3, the lone pair of nitrogen is not that much electronegative because the percentage of S character in NH3 is less, but percentage of S character in pH3 is around 97%. It is very high. If percentage S character in pH3 is 97% very high, it will not like to give its lone pair to H plus. So the reaction with HCl is not possible in dilute condition. But in concentrated condition, it is very less possible. But in case of ammonia, it is strong base. It is ammonia is base and can react with HCl. Among organic bases, compared to organic bases, ammonia is strong base. Compared to inorganic bases, ammonia is not that much strong base. So we say ammonia is base. We can say ammonia can react with acid in dilute condition. But pH3 cannot react with acid in dilute condition. Then evidence number 2, I tell you. Suppose you take ammonia and form coordinate bond. In coordinate bond, ammonia can act as ligands, and these ligands of ammonia can form many coordinate compounds like CO, NH3, 5, Cl, Cl3. But there is no coordinate compound using pH3. If pH3 is strong base, if pH3 has ability to donate the lone pair and forming coordinate bond and acting as ligands, then it can form coordinate complex, but it will not form any coordinate complex. So why pH3 does not form coordinate complex? This is explained by Drago's rule. In pH3, the lone pair is highly electronegative because percentage S character is very high in pH3. But percentage of S character in ammonia is less. So ammonia is stronger base than pH3. If ammonia is stronger base than pH3, then ammonia can form coordinate bond, but pH3 cannot form. So these facts can be explained only by using Drago's rule, where there is no hybridization is possible in these cases. So like that, we have taken the other cases, that is in case of water. In case of water, H2S, H2SC, H2T. There will be no hybridization for this case, no hybridization. Bond angle is 90 degree, so no hybridization. So how this bonding is possible, let us take. Now sulfur atomic number 16. 1s2, 2s2, 2p6, 3s2, then 3p4. So in this case, 3s2 having 2 electrons, 3p4 is having 4 electrons, like this. Suppose hybridization is there, then sp3 all will mix and hybrid orbital is formed. Now you assume that there is no hybridization. If there is no hybridization, you will get pure p orbital, py and pz are pure. If py, pz are pure, then py and pz, or px and py, or px and pz, these are interchangeable. Okay. So we are taking py and pz, they are pure orbital. So these are the two pure orbital, py and pz. So if they are py, pz, pure p orbital, then only they can lie with an angle close to 90 degree. If they lie angle close to 90 degree, then your two hydrogen can overlap like this. This is hydrogen, this is hydrogen. And these two lone pairs are pure. So these two lone pairs will be there, and that will be pure. Okay. two lone pairs will be pure, that will be there inside. So there will be pure lone pair and there will be no hybridization for this. Now question arises, if hybridization is not there, the bond angle will be exactly 90. Why the bond angle is close to 90, 91 degree, 92 degree, 93 degree, 90.5 degree. Why this is coming? See, there is no hybridization we are telling. This is not 100% correct. Hybridization will may take place up to small extent. This is empirical rule and this rule is not 100% correct. But this is an assumption that there is no hybridization. If there is no hybridization, then only we can take the bond. We can explain the bond angle is close to 90. Number one. Number two, we can explain about the basic strength. So if you see the basic strength of water and H2S, then acidic strength of water and H2S, then the basic strength of water, if you see, water is stronger base than H2S. So if you see coordinate complex is possible from water, but coordinate complex is not possible from H2S because water can act as donor, because water being stronger base than H2S can act as donor and form coordinate complex. So water can form coordinate complex and many coordinate complexes are there. So say ApH2O5 NO SO4. So H2O can form coordinate complex like this, but H2S rare does not form coordinate complex. Why? Because this is weak base. And this weak base is because in H2S the two lone pairs are pure S orbital. The percentage S character is more. Out of two lone pair, one lone pair is S. So more the percentage S character, more the percentage S character, more will be electronegativity. More the electronegativity value, more will be acidic character. More the acidic character, less will be basic character. So these things can be explained only by Drago's rule, nothing